Hello, everyone. Good morning, good evening, good afternoon, depending where you are. My name is Shengkai Wang. I'm an assistant professor in mechanical engineering at Peking University in China. It's my great pleasure today to serve as Combustion webinar co-host today. Allow me to introduce our speaker. We are much delighted to have Dr. Weiwei Cai from Shanghai Jiaotong University today to share his exciting research on five-dimensional imaging for combustion diagnostics. Dr. Weiwei Cai is a research professor in the School of Mechanical Engineering at Shanghai Jiaotong University, commonly known as SJTU. He received his PhD from Clemson University in 2010. Before joining SGTU, he worked at the University of Cambridge from 2013 to 2015 as the Marie Curie Fellow. His research mainly focuses on computational imaging techniques for combustion diagnostics, including tomography, holography, and spectral imaging. So with that, Weiwei, please, I'll give the floor to you. And for those of you in the audience who have questions, please type them by chat or Q&A function. We're going to handle your question to the speaker after the presentation. Thanks.
Great honor that I can introduce some of my work for the past few years in this very prestigious combustion webinar. So the topic today is toward five-dimensional imaging for combustion diagnostics. So first, let me briefly introduce my institute, Shanghai Jiaotong University. This university is located in Shanghai, and it's a top university in China. And the major in mechanical engineering and aerospace engineering is quite strong here. We have very good students, so it's really nice to work here. Currently, I'm also hiring postdocs, so if you are interested, you can contact me. So let me first introduce the background, because you all have background in combustion, so I won't talk too much. So one thing I want to emphasize is why I want to do five-dimensional imaging. Okay, this is because the requirement from the measurement of engines combustion. Because the situation for engine measurement is quite difficult. For example, the flame is highly non-uniform and it involves multi-species. And also the temperature is very high, pressure is very high, and the velocity is very high. So we need multi-dimensional imaging techniques. Here is a classifications of diagnostics, not just optical. All kinds of diagnostics, including intrusive and also non-intrusive. For non-intrusive, we have acoustic, electrical, and optical. For optical measurements, we have spectroscopy and non-spectroscopy techniques. And for spectroscopy techniques, we have the chemiluminescence and the laser spectroscopy. So all various of methods we can use. This figure illustrates the evolution of optical diagnostics. There are different ways to describe this, but here is described in terms of spatial resolution from point measurement, 0 dimension, to 2 dimension, PLIF, for example, and 3 dimension where you combine tomography or you do laser sheet scanning. Also 4 dimension imaging. So when you add a temporal dimension into your measurement system. So the next stage will be the 5-dimensional imaging techniques in which you add a spectral dimension into your measurement capacity. So because the measurement sensors, the detectors we have, for example, we have camera. So a camera can only record 2-dimensional information. So if you want to get a higher dimensional information, you need processing of the data you have. That's why we need computational imaging. So when you do computation, that means that you increase the complexity of your data processing. The benefit is when you increase your investment in computing, then your requirement for the equipment will be relaxed. That's the benefit of computational imaging. So my group has developed various of techniques, including VLEAF, CTC, background-oriented Schreierian tomography, incandescence tomography, holography, and spectral imaging. So I will briefly introduce these techniques today. So first, let me introduce what is tomography. So tomography is an imaging technique. It's an imaging technique that can see internal structures. Okay, so typically imaging techniques can only, for example, if you're using a camera, you can only see the surface of an object. But if you want to see the internal structures, you need to do tomography. So the definition of tomography is a reconstruction from a function or a function from its integrals. So the first step is to find a quantity that is an integral. So let me show you an example. For example, absorption. So absorption is a line of sight technique. The absorbance you measure is a line of sight integration of the absorption coefficient along the line. So it's a quantity that is integratable. So this quantity can be recovered using tomographic technique. Okay, so we can do absorption tomography. To illustrate the tomography in a very intuitive way, here I illustrate the example. For example, we have a chessboard here, and we can place different chassis on the board, and we assign different values to this chassis. Then we can sum the quantity along the horizontal direction. Then we get a bunch of line of sight integrations. And this assemble of line of sight integration is called a projection. This is a horizontal projection. If we sum this quantity along the vertical direction, we get a second projection. We can also do the summation along various of angles, and then we can get a bunch of projections. And if we put these projections together, what we get is called a sinogram. Okay, it's called a sinogram. It's essentially a two-dimensional picture. Now, if we remove all the chassis on the board, and we only know the this sinogram, how can we recover the places of this chassis on the board? Okay, that's the inverse problem. That's the mathematical problem of tomography. So essentially, each pixel in this sinogram essentially provides a equation, and the sinogram itself is an equation system. So if we can solve this linear equation system, we can get the distributions of these chassis on the board. Okay, this is a problem of tomography. So let me explain in a very intuitive way how to solve such a inversion problem. So if we take a 2x2 example, we have 4 variables, and we know the projections along 2 directions, horizontal and vertical. And so the first step is shoot a guess. It can be arbitrary solution. So we guess 0, 0, 0, 0. Then we sum up along the horizontal direction to get the projection. And you find that the projection does not agree with the real measurement, which is 3 and 7. So there is error, which is 3 and 7. So we divided the error by 2 and add to the pixels along the horizontal direction. This is called back projection. Then we updated the values of the pixels as shown here. 1.5, 1.5, 7.5, 7.5. Then the horizontal projections are corrected. And then we check the vertical projections to see whether the vertical projections are correct or not. Unfortunately, it's not correct. Then we have to correct the values along the vertical direction. So again, we divided the areas by 2 and add up to the pixel values. Then we updated these values again. Now we sum up along the vertical and also the horizontal directions. We found that this time the projections agrees with the measurement. Then that's the true solution of this problem. How to understand this process in a geometrical approach? Okay, assume we have 2 equations, and the solutions would be the intersection of the 2 lines defined by these 2 equations. Okay, so first we take an arbitrary guess. The solution is f naught here. Then we do the projection to the line S1. So through this way, we can make our solution agrees with the first equation, but it does not satisfy the second equation. So we do another projection from P1 to P2 to make it satisfy the second equation. But now it's not satisfied this first equation, so we project back to S1. So iteratively, we will converge to this F. That's the final solution. And this is the interpretation of the so-called ART algorithm, which is widely used in tomography. I see some questions. I will answer all these questions after my talk. And also, when you have many equations, you can iteratively project your solutions. So in this way, once you finish one cycle, it's called a projection. It's called a iteration. And you stop until some criteria was met. Okay, this is how the ART algorithm works. Also, you can group the equations, and you can iterate between those sets. This will speed up the convergence. Okay, so because we are solving a linear equation system, so the relationship or the correlation between the equations are very important. So how to reduce the correlation between these equations is a big problem. So how to do that? We can define the angle. So we can calculate the angle between the vectors, which is defined by the rows of the weight or the weight matrix. Okay. So if you calculate the angle of these 2 vectors, if it's 2 pi, then that means that these 2 vectors are completely independent. That means they are orthogonal to each other. If these 2 vectors are parallel to each other, that means they are completely linearly correlated. So these 2 equations does not provide any useful information. They are just redundant information. So to do that, to reduce the redundancy, we need a criteria for that. So we proposed a matrix, which is called matrix of orthogonality. Okay, so in this matrix, each element is the angle between 2 vectors. So each vector defines the position of a laser beam. And we can convert this problem into an optimization problem. So if we can maximize the smallest element in this matrix, then we can make any 2 vectors to be as independent as possible. So here is the comparison between these parallel beams, and this is the fanned beams, and this is the optimized beams. And we do some simulations to see whether this method works or not. And you can see on the right is our results. And here is the results obtained by parallel beams and also the fanned beams. And here is the phantom. So we calculated the error. We find that the optimized ones has the smallest reconstruction error. So this method can maximize the sampling efficiency, spatial sampling efficiency. But is there any other ways to increase the information we can get from the tomographic measurement? The answer is to increase the spectral sampling. For example, if we measure at 3 different spectral features, then we get 3 sets of equations. So we get more information. We should have better reconstruction. The problem is we increase the number of wavelengths. We will also increase the number of sets of variables. And the variables are different from different sets. So because the absorption coefficient is different at different wavelengths. So how to solve this problem? The solution is that instead of solving the absorption coefficient, we directly solve for temperature, pressure, and the concentration of absorbing species, because this is a common variables of this or the absorption signal. So we can convert the non-simultaneous linear equation systems into a simultaneous nonlinear equation system. And by solving this nonlinear equation system, we can simultaneously get the distribution of temperature, pressure, and the species concentration. So based on this idea, we propose the concept of nonlinear tomography. So in nonlinear tomography, the line of sight integrated signal is nonlinearly dependent on the distribution or the physical quantity you try to reconstruct. Okay, so by turning or by changing the wavelengths, you can get different sets of nonlinear equations. So now the next sinogram you can have is 3-dimensional. The third dimension is just the spectral dimension. So that's the one benefit of nonlinear tomography. You have a sinogram which has a higher dimension. So how to solve a nonlinear equation system? There are many ways to solve it. And the most simple one is to do optimization. So we can have the measurement term, which is you need to you need to make sure that the solution you have will produce the signals that agrees with your measurement. And also you can include some prior informations such as the smoothness of the distributions of the physical quantities. And the best solution should be balanced between these two. So based on this, we successfully simultaneously reconstructed the temperature, species concentration, and the pressure. So nonlinear tomography is a mathematical concept, but it's not just a technique. So it can combine with different measurement techniques, line of sight measurement techniques, to enable the spatial resolution. For example, acoustic tomography. So here is the review paper for absorption tomography, if you are interested. And also people trying to do volumetric absorption tomography. For example, Professor Spearing from UCLA, they also did some great work on this. The problem is they require a high-speed infrared camera, which is really expensive. So for multi-dimensional, for multi-angle measurement, it's really expensive. Okay, so now let me introduce a little bit about chemiluminescence. Okay, because in chemiluminescence, we don't need lasers, so it's much more simpler. We just need cameras. How it works. So for example, here is the region of interest and the flame is contained here. For each light point source, it will produce a point spread function on the camera. So if you have a second point, the image on the camera is just the 2 PSF. And if we have a third one, then it's the final image is a summation of 3 PSF. And if we have infinite number of point light sources, then we have the flame image on the camera. And we can mathematically summarize this process as the equation here, which is also a linear equation system. So this is also a tomographic problem. But instead, in absorption tomography, the signal is light-outside integration. But here, the signal is not a light-outside integration. It's a integration over a volume, because for the signal at a specific point on the camera, it can be generated from a volume of light sources here. So it's not along a line, it's along a certain volume. But it's also integration. So based on the principle of tomography, we did some measurement of swirl flames. This is for a high-speed swirl flame measurement at 4K. So this is already 4D measurement. One challenge is that when we do some studies of thermoacoustic instability, then we contain the flame within the cylindrical glasses. And sometimes at high pressure, the cylindrical glass is really thick. So the refraction on the inner and the outer surface of the cylinder is really mess up the projections, and the reconstruction would not be successful if you use simple pinhole model. To solve this problem, we integrated the Snell's law with the pinhole model to solve this problem. This is a collaboration with an Italian group. Once we developed this method, we try to reconstruct the single flame within an annular swirl burner. This is in collaboration with Nicholas Wurst, Professor Nicholas Wurst. And here's some preliminary results shown on the right. This is a phase averaged measurement. What we did is we use cameras to measure at 27 different angles, and we get 27 projections along the horizontal plane. Then we do the phase average, the reconstruction. So the problem is, because we don't know the real structure of the flame, so how do you validate whether your method is correct or not? So the approach we used is we take a picture of the flame from the top of the annulus burner. So this is the picture taken, and on the right is the projection we estimated from the reconstruction along the vertical direction. So if we compare these two, if these two agrees, then the reconstruction is reliable, because this projection is not participate in the reconstruction. Also, we can combine CTC or tomography with two-color pyrometry with it. So the tomographic part is the same, but you only need to post-processing to get the temperature. We also did some relief measurement just using one single camera. We designed this 9-in-1 fiber bundles. This design was first proposed by our group and fabricated in Nanjing company. And since then, it has sold very well. So they become rich in China now, because in China, many institutes and companies buy products from them. They're just using one single camera to do volumetric tomography. Let me introduce a little bit about plenoptic imaging, because people are trying to use this for volumetric flow imaging, but this is not a good idea to me, because let me first introduce what is plenoptic imaging. So in a regular camera, a point light source will be imaged to one single point if it's perfect lens. Then you can see that the rays from different angles converges to one single point. So the angular information is lost because you image it to one single point. But in plenoptic imaging, you put an array of micro lenses in front of the sensor. So different rays from the same light source will be imaged onto different pixels. So the angular information is recorded here from the detector. What's the problem with plenoptic imaging for flame measurement? The problem is, even though the angular information is maintained, but the angular difference is really small. The maximum angular difference is about 1 degree. So these projections at different angles is very similar. If you take a look at the sinogram, for the measurement, as we see previously, we use fiber bundles. The angular difference is about you can see here about tenths of degrees. But here, the angular difference is just 0.1 degrees. So there is so much redundant information, it's almost impossible to reconstruct the continuous flame. That's why it should not be used for flame luminescence imaging. So to validate this idea, we did some measurement. The first one is we use three different mirrors and prisms to image from 3 different angles, projections from these 3 different angles to the plenoptic camera. So we essentially have 3 plenoptic camera here equivalently. And then we can do tomographic reconstruction. So let's take one step back to say how we can first to extract the projections from one single plenoptic image. The principle is like this. So here is the plenoptic camera. The pixels are the sensor, and the circles and the micro lenses. So for each pixel behind the micro lens, for example, we labeled 1 here. The first pixel here, the first pixel here, and the first pixel here, first pixel here. We put them together, it forms the image. This is the projection of the flame from the same angle. Okay, if we do the same for the second pixel, we'll get a second image, a third pixel, third image, fourth pixel, fourth image. So while this way we can extract 100 of as much as 100 projections, but these projections are very similar to each other because the angular difference is really small. So we did some reconstructions with 3 projections. So each projection is selected from 3 different angles. So we have 3 projections here. And we also select 4 projections from each angle. So we have 12 angles. And also we reconstruct using the projections, all the projections at one single angle. So we compare the quality. This is a reconstruction of a candle flame. So you can see that when you're using one angle, the reconstruction is really bad because you cannot resolve the real structure of the flame. This conclusion is also supported by the review article written by Professor Brian Thoreau. So if you are interested, you can check this review paper. We also did some non-luminescence tomography, for example, background-oriented Schurerian tomography, how it works. So we have a background plate here. On the background plate is random dots. Random dots. If we have the flame, and if we don't have the flame, the dots on the imaging plane, the position of the dots on the imaging plane will be different, because when the flame is on, the refractive index distribution of the flame will change. So that will refract the light toward the different places. So by comparing the displacement, all these dots, we can combine it with tomography to reconstruct the distributions of the gradient of refractive index. Also, we can make it high speed by using just one single camera with a fiber bundle. The reconstruction, the computational time for one single frame is really huge, because the number of variables involved is enormous. It's about 1 million or above variables for each reconstruction. So it takes several hours to process one frame. To reduce the computational cost, we try to use deep learning algorithms to speed up. So here is some results. So the principles I want to introduce, because it's quite straightforward, and it's also a very hot topic now. I will just show some results. The quality is quite good if you're using deep learning. The other application we use deep learning for flame processing is very interesting, I think. This one we use deep learning to predict the evolution of flame. So what do I mean? So we have a neural network here, and on the left, in the feed in, we have a series of history 2D images, and on the right is the future 3-dimensional flame structure. So we establish the relationship between the history data and also the future data. And by this way, we can predict the evolution of the flame. Here is the results. On the right is the ground truth, and on the right is the predicted flame structure. You can see they agree quite well. It has some potential applications. For example, you can use this technique to optimize the operation of boilers, coal-fired boilers, to optimize the combustion efficiency. Okay, now we enter the topic of 5-dimensional imaging. For 5-dimensional imaging, we need a high-speed spectral camera, which means that this camera can have the spectral information of the spectral dimension. And the problem is, on the market, we don't have high-speed, spectral camera, so we need to build one by ourselves. How to do that? That's the topic, one of my topic recently. So the typical spectral camera on the market that principle is listed as follows. So typically, people using point scanning or line scanning method to scan the scene, or to scan the flame, but the flame is changing rapidly. So in this way, you cannot capture the instantaneous flame. So we need to capture the spectral image of the flame at one single exposure. So how to do that? So here is the example. Here's the image, which is colorful, as you can see. That means it contains many wavelengths. And if we expand the color along one direction, like this, and then we have a three-dimensional date cube. So mathematically, it's just a three-dimensional date cube. It's the same with the flame chemiluminescence at one single wavelength, because that's also three-dimensional date cube. This is the same. This is also three-dimensional date cube. So how do you reconstruct a three-dimensional date cube? You just try to do tomography, right? So if you can get the projections, of this date cube along different angles, then you can combine it with tomography to recover this date cube. So how to do that? If you have one camera here, you have 4 pixels, for example, and you have 8 voxels here, you try to reconstruct this date cube. Then you can have an equation system. So P1 is the summation of the signal of these 2 pixels, or these 2 voxels, and P2 the same for these 2 voxels. Then you have an equation system. But the problem is these equation systems are not correlated because they don't have common variables here. So you cannot solve this equation system. So how to do that? You get another projection. Okay, you get another projection, for example, along this direction, 45 degrees. Now the signal, you put another camera here. The signal on this camera is like this. Okay, it's another set of linear equation system. And if you combine these two together, you will find that now the variables are correlated. So by solving this equation set, you can get the entire date cube. But the 2 projections are not sufficient. You need more than 2 projections. So how to do that? It's very simple. In a regular camera, in front of a regular camera, you put a 2-dimensional grating. Okay, you put a 2-dimensional grating here, and due to the diffraction, the date cube will be dispersed along different angles. Okay. So, for example, as you can see here on the right, you have 25 projections. And by combining with tomography, you can reconstruct the hyperspectral date cube. It's the same technique with 3D, with CTC. The mathematical is completely the same. The benefit of this and the advantage of this technique is that you get the entire spectral cube, date cube, in one single exposure. Okay, so you can instantaneously get the spectral information of the flame. So we did a validation first by imaging a known object. We know this the spectral of this figure, and we compare this with we compare the reconstruction with the measurement from spectrometers. Then we can validate our method whether it's correct or not. Then we can do 5-dimensional imaging, and this is the results for 5-dimensional imaging. We call it a cascade tomography because the first step is you need to reconstruct the spectral image spectral image for different angles. Here we use 6 angles. So the first step, we need to get the spectral images at different angles. And then we pick out one single wavelength, the projection at one single wavelength, and do the regular CTC tomography. Then we can reconstruct the flame distribution at one single wavelength. So if we repeat this process for all wavelengths, then we can get the distribution of the flame at all wavelengths. So by this way, we can realize 5-dimensional imaging. But here, remember that we need to use high-speed camera. So as I mentioned, you can use tomography to do that, but you can also use compressive sensing to do that. For example, here's 2 equations. These 2 equations, you can have the weight matrix like this. And if you calculate the condition number is this. And if you have another set of equation system like this, you can calculate the condition number, that's 1, right? So that's the condition number is much better than this one, because these 2 equations are completely uncorrelated. So when we design a weight matrix, we should design a weight matrix has a very small condition number. So how to do that? So for example, if we have a weight, one row of a weight matrix, which is sort of random numbers of 1 and 0, okay, 1 and 0. And if we shift this vector by 1 position, and we calculate the correlation of these 2 vectors, the correlation will be very small because this vector is random, right? Because this vector is random. So based on this idea, we can design a mask which has random white and black pixels here. So when we pass this hyperspectral day cube via this mask, and then we use a disperser to disperse these different wavelengths. For example, using 1D grating, we disperse this and we sum it up. We can get a set of equations here. Okay, and for this equation, the weight matrix is very good because the rows are random, so their correlations is very small. So by this way, we can also do reconstruction of the spectral day cube. And this method is called a coded aperture. I won't go to details because we don't have much time left. Based on this similar technique, we can do ultra fast imaging. But in this technique, instead of disperse the spectral dimension, we disperse the temporal dimension. So it's also a 3-dimensional day cube, but the third dimension is temporal dimension, so that we can resolve very high speed phenomenon. This technique is used to image the travel over light pulse. I won't go to details. Another approach is to build an array of miniaturized spectrometer. And this is a work we collaborate with Cambridge University. We fabricated a nanowire which can be used for a spectrometer. So this is a nanowire, and this is the it's called gradient compositionally gradient nanowire. So on the left it has one alloy, on the other end it's another alloy, and in the middle it's a gradient change of these 2 compositions. So that the band gap along this nanowire changes. That also means that the spectral response of this nanowire changes along this line. So if we make electrodes along this line, and each 2 electrodes constitutes a detector, then the nanowire itself is a detector array. but the response to the light is different. So if you have a light shine on this nanowire, you can get a set of signals. You can get a set of signals, and then that signal can be formulated into a set of linear equation system. Then solving this linear equation system, you can get the spectra of the light. Okay, this is the the principle of this technique. So you have a linear equation system, and solve this linear equation system, you get the input light. But the system, this inversion problem is much easier than volumetric tomography, because you only have tens of variables, but in volumetric tomography, you have millions of variables. And this is a review paper we published on Science, summarizing all these computational or reconstructive miniaturized spectrometers. The principle is very similar, but you just using different types of materials. Another topic now it's very hot is matte surface. Matte surface contains structures that has various sub-wavelength structures, and these structures can modulate the light just like a filter. So just like a nanowire, the nanowire, you have different spectral responses at different positions. Here is the same, but it's just using sub-wavelength structures to do that. And by this way, you can just using a flat glass, very thin glass, that you can construct a spectrometer. And if you do an array of this, a matrix of this, then you can get a spectral camera. This is another technical approach. And based on this approach, we build up a very small spectral camera. We can further reduce the size of this spectral camera. And we can build a few of those cameras, and we can do spectral tomography. So let me summarize the talk. It's almost the time. So first, the tomography. One thing is that is the accuracy of tomography. So how you validate that is whether the value is reconstructed is correct or not, and also the spatial resolution. How do you define the spatial resolution? This is a difficult problem. And also the measurement under harsh environments, and also this is a really interdisciplinary nature, because it involves optics, material science, machine learning, combustion, so all kinds of disciplinaries. So that's all my talk. Thank you very much. So I want to thank my students, Dr. Tao Yu. Now he's in KAUST, Mr. He Tong Liu and Jianqing Huan. So all these are my students. And on the right is my collaborators. And we thank all these collaborators. And also I want to advertise that I want to hire postdocs. If you are interested, please email me. Thank you very much. So I will take questions.
All right, thank you very much, Dr. Weiwei Cai, for a very nice talk. This talk is the speaker is open to questions, and for those of you who are who want to ask questions, please feel free to directly type them in the chat room.
First one is Professor J. Gore, but the question is pointing out that it's a ill-posed mathematical problem. Yes, I agree.
What I mean is, if your solution is iterative, because it's essentially you're trying to find the variable from the function, and if the solution is iterative, you have a set of initial guesses that you start with, and if those guesses are off, then the solution can diverge. You can get very images, the reconstructed images that have very little to do with the original image. And mathematicians have proved that how the problem can diverge.
Yeah, So you mentioned that the solution is dependent. The final solution depends on the initial gas. Or
no, whether the solution will converge depends on the initial gas. Any solution that depends on the initial gas is, of course, not a solution. By definition, it's not a solution if it depends on initial gas. Solution should be independent of the initial gas, right? They should converge to the actual solution rather than depend on initial gas. But maybe we can take this offline. Thank you.
Yes, so I add one comment because for our combustion measurement, for most cases, it's undetermined problem. So we have infinite number of solutions. So you start from a solution. Probably you will converge to some different solution if each time you generate a different initial gas. Yeah. Okay.
Yeah. Thank you. Mm-hmm.
So when you, especially regarding your work on the plenoptics, so how do you make sure that all the pixels from different point of view line up? Do you have a kind of automatic calibration method, or?
You mean for the method we use camera, or we use
the fiber bundle work?
Oh, the fiber bundle works. You mean how to match the fibers with the pixels, or is that what you mean?
No, so it's mostly about a physical point in the space. It shows up as multiple points in different field of view, right? From different angles. How do you correlate those pixels to the same point?
That's done by calibration.
Right. Do you use a calibration mesh or something?
There is a very mature tool that you can use a calibration plate. You can plate the calibration plate. You can place the calibration plate in the middle of the volume you want to try to reconstruct, and you take the calibration plate simultaneously with different angles. Then you can establish the relations. Yeah.
All right. Thanks. I see no further questions, and it's already about the time limit. So thank you again. So due to the time limitation, so we're gonna pause here. If any one of you have any further questions, I'm sure that Professor Weiwei will be glad to take them offline. Thank you again for joining this webinar.